Hello. In this video, we're going to revise some of the concepts that we've discussed in previous videos to discuss the relationship between fractional flow and the solution to the Buckley Leverett equation, relating again that to wettability, but also to the solution of the equations and to recovery. So to do that, what I've done here is I've prepared, as you can see on the screen, okay, fractional flow curves for three types, our three generic wettabilities. In a previous video, I've shown the relative permeabilities as well, but I think hopefully we can understand what these look like. So let's take the strongly water wet case. If it's strongly water wet, as we know, the water goes into the narrow regions of the pore space, so the water fractional flow begins to be low. And then if you remember what the relative permeabilities look like, the oil relative permeability drops very sharply. We have a relatively large residual oil saturation. And what that means is the fractional flow of water, if the oil relative permeability goes down, the fractional flow of water will go up. And so the fractional flow of water rises steeply. So typically for a strongly water wet case, you can have a fractional flow that looks like this. So now let's imagine that we try to do the Buckley Leverett solution. So what we do is we get our a straight line and we try and draw a tangent to the curve, and we find there's no tangent. Okay? And in fact, the solution, right, as shown here, is all shock. There's a shock from 1 minus SOR to SWI. There's no rarefaction. There is, in fact, no tangent at all. Okay? So it's the all shock case. Now, sometimes people find this confusing or difficult. It's actually a really easy case, isn't it? Right? Just all shock. And so now, if we were to look at the solution, so if instead on this axis I had saturation, and on this axis I had velocity, then what you would find is you'd find a solution where this is the maximum saturation, 1 minus SOR minus SWI. Okay, we have a shock, okay, that's moving at a speed which is the slope here. Well, it's 1 divided by the change in saturation. And so our solution is a constant state and then a shock, okay? And the shock is going at that speed, okay? So we have a constant state here. Maybe I could draw it as a proper straight line, so that's a bit more evident, okay? And then we have a shock, which is another straight line, okay, like that. Maybe that's a rather neater way of drawing it, okay? So we have a constant state and a shock, and that's the speed of the shock. And then if we were thinking about a recovery curve, so I know this is going to get rather busy, this diagram, but if we were to put on this axis MPD, maybe I should do it in a different color so that's a bit more evident. Okay, if this was MPD against TD, okay, we just have a linear change, okay, so here, and then a constant. So this would be MPD equals TD, okay? The maximum recovery is 1 minus SOR minus SWI, so it's in fact following this, okay? And this point will again be a TD, okay, which is 1 minus SOR minus SWI. So I agree it looks quite busy, but the solution is relatively straightforward. Okay? It's all shock, there's just a shock. The front is a constant state in the shock. So when you're recovering oil, you're producing oil, then the shock comes along, bang, you go to the maximum saturation and there's no further recovery. So it's the simple case. Again, don't overthink it, it's the simple case. And this is classically what you see in water wet rocks, is you're producing oil, and then when the water breaks through, you go immediately to the residual saturation. So the residual saturation might be high, but you get there without producing oil and water together. So it's actually very efficient. Now let's go to this case. Okay, let's talk about the oil wet case. Let's look at the one, let's say the opposite case. Okay, so we're going to do the same. Okay, this is oil wet. Now, if it's oil wet, the water goes through the big pores, so the fractional flow rises steeply. And then we have a large region near 1 minus SOR, and SOR is low, where the oil is just flowing in layers, right? There's virtually no oil flow, so the water fractional flow is very close to it. Okay? So we have a curve that looks like this. It's got the opposite curvature. So now let's imagine we try and do our shock construction. We can't, right? Because the tangent, right, is sort of here. It's right at SWI. So in fact, there's no shock at all, right? It's in fact just the velocity here. If we actually get rid of this, it's a bit misleading, in fact. Okay, if we draw this, the velocity, the dimensionless velocity is simply dFW by dsW. Okay, it's a maximum here. It's not infinite. It's just some maximum large number, and it goes down to 0. So if we were again to plot the solution here, SW, this would be 1 minus SOR minus SWI. You'd have a large region, and this would be VD. You'd have a large region actually with a very low velocity like this. Okay, this would be SWI. Okay, and so you'd find a solution that would look like that, and there'd be no shock. And this maximum speed that we move at, the max, okay, will be the gradient here. Okay, so the gradient here, right, the FDS here will be this maximum velocity. Okay. And there's just one thing I need to draw in the previous graph, so maybe it was a bit misleading when I showed the saturation. Of course, there is SWI, so the shock doesn't go to S equals 0, it goes to SWI here. In fact, the shock did that to SWI. Okay, it's just a shock. The recovery starts at 0. So there is an initial water saturation in the solution. Okay. Now let's look at the intermediate case, which we've already shown is not intermediate. Okay, the mixed wet case. Okay, what happens if it's mixed wet? Well, if it's mixed wet, we said, okay, the water to begin with can go in some of the smaller pores and some of the larger oil wet pores, but the water is poorly connected. Okay, so the water's filling some larger areas, but they're not well connected because they're just little bits, patches throughout the rock. And so in fact, the water fractional flow stays really, really low. Okay, so it's really, really low here. Eventually, it does get up to 1, and we get this oil layer drainage regime. So the only way in which we can sort of connect this region to this region is with an S-shaped curve like this. So this is classic Buckley Leverett. Right? So most people have least difficulty with this case because it is, you know, what it seems to be in the textbooks. Okay, I try and draw a tangent here. Maybe not the best tangent. That's better. Okay. Okay, this point represents the shock. Okay, so we can have a shock here with a slope, okay, that's this distance. This is FW left, right, and the shock is FW to the left over SW to the left minus SWI. Okay, and the shock and the solution will be, I might say, a classic looking Buckley Leverett. Okay, there will be no constant state to begin with because the velocity here is typically 0. Okay, so we'd have a rarefaction and a shock. And because this is going to be busy, and I've shown it in a previous slide, I'm not going to show that because that's the classic case. Okay, so you know, you're worried about, oh dear, what's that going to look like? It's going to be something strange. So just pick up the textbook. It's the one there. Okay, with the S shape and a shock and a rarefaction. Okay, so that's the classic case. So now if we look at these solutions, as I said, the water wet case, although we've got a high residual oil saturation, is actually very efficient because you just have this shock moving along. Okay, so there's just oil production, and then as soon as the water breaks through, sort of, I would say it's game over. The oil wet case is clearly very bad because you have a leading waterfront that's moving very rapidly. This is a high gradient here. Okay, so this moves rapidly. You get very early water breakthrough, but without a shock. So you start producing a little bit of water, then a little bit more, then a little bit more, then a little bit more, then a little bit more. So in order to produce the oil, you have to be recycling lots and lots of water. And so that's inefficient. In theory, eventually you can get down to a low residual oil saturation, but you have to inject hundreds, if not thousands, if not tens of thousands of pore volumes of water. So you could do it in the lab, but it's not something you see in the field. In the mixed wet case, you have a combination here because yes, there is a shock, okay? And then there is a rarefaction. So whether or not the mixed wet case is the most efficient really depends on the shock height, right? So it will depend on the specific case. Sometimes a mixed wet medium can give you very favourable water flood recovery, because even when the shock comes, you've actually recovered quite a lot of the oil. Okay, but it does depend on the case, right? Don't grab hold of a sort of little simple mantra: mixed wet good, oil wet bad, water wet in between. That may be the case, but it's not always the case. It will depend on exactly what the relative probabilities are and what the mobility ratio is. Okay, but this is how you construct the solution. So it's a simple schematic here. I don't want to say any more. Okay, I hope that's been reasonably clear. Okay, so I'll finish that now. I hope that's helpful for you to see that relationship between wettability, the fractional flow, and then how you might go about constructing the solutions. And yes, there are some cases where you don't see everything. You can have a case that's all shock, and in fact, you can also have a case that's no shock at all. Okay, thank you very much.